Now I know that the desire of your heart, you have been just sitting here hungering and thirsting for the chance to do stoichiometry with gases. What more could you ask? And of course, the map makes that possible. Sorry, it's kind of crinkled up. The cat decided to sleep on it. All right, notice that we can start with the volume of a gas. See that little red word gas there? We can start with the volume of a gas and change it to moles of gas, either by using the ideal gas law, PV equals nRT, and this will not be dimensional analysis. This will be solve the equation for N, and there you go. Or we can do it in two steps. If you like the combined gas law better, then you can use P1V1 over T1 equals P2V2 over T2 to change this from whatever pressure and temperature it was actually at to standard pressure and temperature. And then, once you know that, you can use the molar volume, which I don't believe we've mentioned. All right, under standard conditions, standard temperature and pressure, 1 mole of any gas will be 22.4 liters, about 5 gallons. Doesn't matter whether it's carbon dioxide or oxygen or neon or whatever it happens to be. At standard temperature and pressure, 1 mole of any gas will be 22.4 liters. So you would have to use the combined gas law to convert to STP, and then use the molar volume and dimensional analysis to convert that into moles of A, and then you can proceed from there. You will get the same answer either way. I promise. It works. So there's really not much to do here except maybe work an example. The stoichiometry map, although it makes things much easier, also makes things a lot more boring. So let's do our example. All right, we're trying to purify some tungsten by reacting it with hydrogen gas to produce pure tungsten and water. All right, let me see. How are we going to do this? Well, let me change colors here just for the sake of separating the problem from the solution. They're asking us for a volume here in liters. And they're telling us that this hydrogen is going to have a temperature of 35 degrees Celsius and a pressure of 745 torr. Well, since this is what they're asking us about, this must be what we're going to call B, just to keep from having to write subscripts all the time. We are told that we have 375 grams of the tungsten oxide. And since we know the amount of that, this must be A. All right, so we know that we're going from mass of A to volume of B, and B is a gas. So we're going from mass of A to volume of B, and B is a gas. So we're going to go whoop, whoop, whoop. But we have two choices of whoop here at the end. All right, so let's set out. We know that, that was supposed to be 835 grams. We're going to start with what we know. We know that we have 875 grams of substance A. We want to get out of grams of substance A and into moles of substance A. And we can do that with the molar mass, which means we're going to have to add up 1 tungsten atom and 3 oxygen atoms. And that's going to give us a molar mass of 232 grams, being the same thing as 1 mole. All right, now we want to get out of moles of A and into moles of B using the coefficients in the balanced chemical equation. Well, the balanced chemical equation is telling us that it's going to take 3 moles of B to react with 1 mole of A. So 3 moles of B to 1 mole of A. That will get us out of moles of A and into moles of B. All right, I can then stop and do this calculation because now I have smacked into this equation, PV equals nRT, and that is an equation, not dimensional analysis, so I'm going to have to stop at moles of B and figure out the volume using that equation. All right, when I let my fingers do the walking on my calculator, I wind up with 11.3 moles of hydrogen, substance B. All right, so now I'm going to plug this in to PV equals nRT. We were told that the pressure of our hydrogen was going to be 745 torr. The volume of our hydrogen is what we're looking for. We now know that we're going to need 11.3 moles. Since my pressure is in torr, R is going to be 62.4. And my temperature is 35 degrees Celsius. Better change that temperature to Kelvin. So add 273 to it and we get 308. So we take our handy dandy calculator, our miracle of modern electronics, and we say 11.3 times 62.4 times 308 divided by 745, and that gives us 291.5 liters. Well, sig figs. We're going to have to give that as being about, we've only got 2 sig figs here, huh? 290 liters. There we go. All right, had we chosen to go the other way, we would have done exactly the same thing right up here to moles of B, and then we would have said 11.3 moles of B, and we know that 1 mole of B is 22.4 liters of B, and so that would come out to be, so to speak, 11.3 times 22.4. That would give us 253.1. And you say, wait a minute, that's not the same answer that we got a while ago. Well, that's because this is not at STP. We're not at standard temperature and pressure. So now we're going to have to use the ideal gas law, the combined gas law, to change this to STP. It tells us that P1 V1 over T1 equals P2 V2 over T2. So 760 times 253.1 over 273 equals, let's see, our other pressure was 745 over 308. All right, now we're going to cross multiply, and so we're going to have 760 times 253.1 times 308 divided by 273 divided by 745, and look at that, it comes out to V2 is 291, or with sig figs, 290 liters. So it doesn't matter whether you use the ideal gas law or whether you convert it and use the combined gas law, you'll wind up with the same answer. The only trick is being sure that you recognize that the STP is what you've found this far, and then you're going into these new conditions that are not STP. All right, if it were me, I'd stick to this. Just easier, less chance of making a mistake. Bye, y'all.